Enzymes are biological molecules, typically proteins, which help reactions in our body to go faster. You'll commonly see them written above an arrow in the metabolic pathways that you'll look at in biological chemistry. So now we know what enzymes are. Let's look at the types of enzymes. So we have oxidoreductases, such as dehydrogenases. So that's a name that you'll commonly see, and basically what's happening here is you'll see an NAD or NADP, an NADH or NADPH, or an FAD/FADH somewhere above the arrow in the chemical reaction, and that's how you know you've got an oxidoreductase going on there. So then we have number 2, which is a transferase. And an example of this that you'll commonly see is kinases, and they involve ATP use/production. So when you see kinase, I want your brain to go, there's an ATP involved. When you see the term hydrolases, when describing enzymes, they involve water in some way. Lyases cut carbon-carbon or carbon-oxygen bonds. Isomerases, also known as mutases, they involve shifts. So an isomer in chemistry is when you've got a chemical that can be seen in different forms but have the same chemical name, or the same chemical, like the same amount of carbons and the same amount of oxygens, for example, in a molecule. So they're the same, but they have a different shape. So that's what an isomer is. So an isomerase enzyme is involved in mutating and shifting the shape of the chemicals that we're dealing with. And finally, we have ligases. For example, DNA ligase, which you'll see when you look at DNA, the formation of DNA. And that's involved in gluing sections of DNA together. For example, DNA ligase. So that's a common one that you'll see. So now we know the 6 types of enzymes. Let's look a bit more about the theory behind enzymes. So let's start off with the term Km. So Km is the Michaelis constant, and basically doing some maths with a graph, they found out that half of the Vmax is equal to the Km. So half of the Vmax is equal to the Km. And from this, basically, from a biological chemistry point of view, what I think you should take away is that a high Km means that the enzyme has a low affinity to the substrate. So what that means is, so we've got an enzyme here, and we've got an active site, which is where the substrate binds. So the substrate is a substance that is binding to the enzyme so that the enzyme can do its work. And affinity means the ability for the enzyme to grab on to that substrate. So a high Km means that it has a low ability to be able to grab onto the substrate, and the opposite is true. So I would just remember what's going on in orange and remember that the opposite is true. You don't really need to know all the maths behind how the fact that half the Vmax is equal to the Km was derived, but I would just remember that a high Km means that it has a low affinity. So now we've got that theory down pat, let's have a look at some different terms when it comes to enzymes, and we're going to look at enzyme inhibitors. So first up, we have uncompetitive enzyme inhibitors. Basically what these ones do are they bind to the enzyme substrate complex, not the active site. So they bind to pretty much the whole enzyme substrate complex, the whole thing, not just what is in hot pink there. So it's binding to that whole complex, and it prevents product release. So it stops the product that the enzyme is trying to produce from being released. It locks it up. But these are pretty rare and won't be found in the body. What you'll most commonly find are non-competitive and competitive enzyme inhibitors. So what non-competitive inhibitors do is they bind to the enzyme at a different site, so not the active site, and they cause a change of shape. And this change of shape is irreversible. And so non-competitive enzyme inhibitors are not what you want to see in the body. And some theory here, non-competitive enzyme inhibitors cause the Vmax to become lower, but the Km to be unchanged. So in that graph that we were looking at before, the Vmax, so that dotted line at the top, would become shifted down, it would be lower, but the Km wouldn't change. And there's some maths going on behind that, but I would just remember that the Vmax becomes lower and the Km is unchanged. And then we have competitive enzyme inhibitors, which bind at the active site, so what's in hot pink there, where the Vmax is unchanged and the Km increases as a result of binding to the active site. So that's enzyme inhibitors. And finally, I just wanted to talk about some other terms that you might see with enzymes. These are allosteric enzymes and non-allosteric enzymes. So allosteric enzymes have an additional allosteric site, which can fit an inhibitor or an activator molecule. So let's pull up a little enzyme again. Basically, it has a different site. So where the green dotted line is, there's another site there, which can fit an inhibitor or activator molecule, and it's kind of like a volume control knob, which can inhibit the activity or cause it to become greater. And finally, we have non-allosteric enzymes, which are your basic enzymes that you commonly see, which just have that active site, and that's all. So that's the terms that I think you should know about enzymes.